This is a tutorial to study Conway's game of life, which is a two-dimensional cellular automaton. It represents a two-dimensional plane of cells where each cell can either be dead, should be represented as a 0, or alive, which is represented as a 1, or if you're using a colored scheme, may be represented as a shaded cell. Now, Conway's game of life defines a particular transition function with the following rules. So the first rule is that a live cell remains alive if it has two or three alive cells in its neighborhood. Where the neighborhood is defined as the group of cells that are within one distance of a particular target cell. So for this alive cell, its neighborhood are these 8 cells. So if 2 or 3 of these are alive in the next time step, a particular cell remains alive. An alive cell will die if there are more than 3, so more than 3 alive in its neighborhood. And an alive cell will die if there are fewer than 2 alive in its neighborhood. So these 3 together are, I'd say, a little redundant. However, the notion is here that in order for a cell to stay alive, it needs to have 2 or 3 neighbors that are alive. Otherwise, it will die. The fourth rule in Conway's game of life states that a dead cell can become alive through a rebirth process if exactly 3 of its neighbors are alive. So we can represent these as, we could draw a transition table. The challenge is that there's 2 possibilities for each of the neighbors. So there's actually a pretty large number of combinations of cell states. A little bit more an easier way of representing this is with like a neighbor function. So rather than having an input for each of the 8 neighbors like we did for the one-dimensional game of life, we could define a neighbor function for a cell in a particular row and column. So let's say this is row I, this is column J. So the neighbor function could count up the number of neighbors that are around it. So in this case, it looks like it would be Q so if this one is QIJ, the neighbor function for this particular cell would be the one in the previous row, I minus 1, and in the previous column, J minus 1, plus the one right above, QI minus 1, J, the one above and to the right, QI minus 1, J plus 1, one directly to the left, which is QI, J minus 1, one directly to the right, Qi, J plus 1, and then the 3 directly below, Qi plus 1, J minus 1, Qi, J, Qi plus 1, J, and then Qi plus 1, J plus 1. So each of these Q values, as I mentioned before, is either 0 or 1. So this neighbor function will take on a value of anywhere between 0 and 8, depending on how many neighbors are alive. So based on this neighbor function, then we could build an easier transition matrix that has the current neighbor value and the current state. And it will tell us the delta function. So this is really x of ij. It's our input. Delta of q and x, which is q at the next time step. So I have to be a little careful here with my notation. This should be q sub ij at time t. This would be q sub ij time t plus 1. So in this particular case, there's still a large number of options. There's 9 alternatives for what n could be. So 0, 1, 2, 3, 4, 5, 6, 7, 8. There's 2 alternatives for what q could be. It's either 0 or 1. So there's still 18 alternatives that we would list in this table. However, we can just represent a couple, for example. So if there's one neighbor and it is alive, we know that it will die. So that falls under this particular rule. There's fewer than 2 alive in the neighborhood. If there's 2 in the neighborhood and it's alive, then it falls under this first rule. We know that it stays alive. If there's 3 in the neighborhood and it's alive, it stays alive. And if there's 4 in the neighborhood and it's alive, it'll die because of rule number 2 for overcrowding. And on the other side of things, if it's currently dead and there's 2 neighbors, you know that it stays dead. But if there's exactly 3 neighbors and it's dead, then it becomes alive through the rebirth process. So we could build up a transition function here. It gets a little bit complicated due to how many cases there are, which is why oftentimes people just describe the transition rules with a number of rules like this. Now to represent a particular game of life initial state, we went over a couple of examples in lecture that had interesting properties. So for example, one of those that we looked at was called the beehive. Right? So the beehive looked a little like this. It had, draw one more here. So it had 2 that were alive, separated by a row, and then with 2 on the ends. Right? So the beehive is an example of what's called a still life. It means that it doesn't change over time. Right? So if we wanted to propagate this to the next time step, the most important piece is to count up the number of neighbors that each cell has. So let's do that in a different color. So this one, for example, has 0 active or alive neighbors. This one has 1. This one has 1, 2. This one has 2, 1, 0. This one has 1 alive neighbor down here. This one has 2. This one has 2 alive neighbors. Right? And this one has 2 alive neighbors. And this one has 2 alive neighbors. And this one has 1. And similar, keep going, keep repeating the process. This cell has 1 alive neighbor. This one has 2. This one has 3. This one has, sorry, this one doesn't have 3. It has more than that. This cell has 1, 2, 3, 4, 5 alive neighbors. This one also has 5. This one has 2 and 1. And through symmetry, we're back to our previous case, 1, 2, 2, 2, 2, 1, and 0, 1, 2, 2, 1, 0. So in this particular case, you can see that all of the cells that are alive have either 2 or 3 neighbors, so they all stay alive. And there's no other cell that's dead and it has exactly 3 neighbors. So to transition this to the next time step, it actually just repeats the same pattern. So the cells that were alive stay alive, and the cells that were dead stay dead. So we can transition this with, or we can compare this with an alternative like the toad, which is an example of a repeater. So it's a pattern that will repeat itself over time. So the toad looks a little bit like this. It has 3 cells in a row that are alive. So 1, 2, 3. And then 3 cells that are alive right underneath, but offset by 1. So if we go through the same process to count up the number of neighbors for this toad pattern, we can say, okay, this one has 0, 1, 2, 3, 2, 1. This one has 1 neighbor here. This one has 3. This one has 4. This one has 4. This one has 2. This one has 1. This has 1 alive neighbor. This one has 1 alive neighbor. This has 3. This has 4. This one has 3. This one has 1. And we can go back. So it has 1, 2, 3, 2, 1, 0. Right. Actually, I made a mistake here. This one, it doesn't have 3, it has 4. Okay. So 1, 2, 3, 4. So based on those neighbor counts, we can then follow the rules to identify the next transition. So at the next time step, right? So any dead ones that have exactly 3 become alive. 0, 0, 1, 2, 3. So this one becomes alive. This one becomes alive. And this one becomes alive. And it looks like this one becomes alive. Any alive cells that have 2 or 3 alive in its neighborhood stay alive. So this one stays alive. And looks like I made another mistake here. This one should have had been 2. Right? It says 2 alive neighbors, so this one stays alive. And all of the other ones that were alive, but they have 4 in them, stay dead, or they die. So in the toad repeater, this is the second state. We get this slightly different pattern. And if we actually repeat this process of counting the neighbors, we'll end up in the next time step reverting back to our original drawing of the toad